practical application, uh, first of all, in the Haber process, we will apply all those four factors one by one. And how we want to apply these four factors, we have to apply in such a way that we want this ammonia gas to be produced on a large scale. Okay. So, what is the objective of industry? The objective of the industry is to produce this ammonia gas on a very in a very large amount. They want a very high yield of this ammonia gas. That's all. Okay. So one of the objective of industry is to produce a large quantity of ammonia gas. So the ammonia gas yield should be very high. And how you will get a very high yield of ammonia gas? By going in the forward direction or the backward direction? By a forward reaction, you will get more and more ammonia gas, or by backward reaction, you will get more ammonia gas. Backward. If you will go backward, you will be getting reactants. I want this ammonia gas to be produced in a large amount on a large scale. So ammonia gas is produced in the forward direction. Na beta? Yes or no? When N2 and H2 will combine, they will be forming ammonia gas. So this is a forward reaction. Yes or no? Ammonia is produced in a forward direction. So what is our objective? Our objective is to take the reaction in the forward direction so that a large amount of ammonia gas is produced. Understood? Yes or no? Are you understanding? And number two, the second objective of industry is that the reaction should be economical. Yes or no? Economical. Okay, whatever the reaction you are doing, it should be economical so that the industry can earn profits from it. Okay, because the main idea of the industry is to sell the product, to sell this ammonia gas, and to earn the profit. That's all. Okay, so they want the process, whole process, to be very economical so that they can earn more and more profit out of it. Okay. And the third thing is that the objective of industry is that they want this ammonia gas to be produced in a very less time period. Okay, they want this ammonia gas to be produced very fast so that they can meet the demands of the market. Understood? They can meet the supply and demand of the market. Is it clear? Yes or no? All right. So we have to apply these three factors in such a way that we can get this ammonia gas in a large amount, in the less time period, and in a more economical way. Okay. So let's start first. We are looking at the factor of change in concentration. So at equilibrium, how we would gonna change the concentration so that we can get the maximum forward reaction? Because when the reaction will go forward, we get more and more ammonia gas. Yes. So how by changing the concentration you can achieve a forward direction? Yes. Okay. Uh, just recall the Chatliers principle. In the Chatliers principle, in how many ways we can disturb the equilibrium? Change in concentration. No? Okay. One was the change in concentration. So by changing the concentration only, how, how by changing the concentration you can disturb the equilibrium? In how many ways you can change the concentration? Four ways, right? Increase in reactants, decrease in the concentration of reactants, increase in the concentration of product, and decrease in the concentration of product. Yes or no? Okay. So out of those four ways of changing the concentration, in which of the ways you get the forward reaction? In which of the ways the equilibrium shifts in the forward direction? Yes, you are right. By increasing reactants, increasing the concentration of reactants, or by decreasing the concentration of product. These are the two ways in which the reaction moves in the forward direction. Yes, sir. Okay. So, if you want to get more and more ammonia gas, so you want a forward reaction. And how you will achieve a forward reaction? Either by increasing the concentration of reactants, okay, or by decreasing the concentration of product. Is it clear? Yes or no? These are the two ways which will take this, which will disturb the equilibrium and will bring this reaction in the forward direction. Okay. So how you will get more and more ammonia gas? So in order to get the maximum yield of ammonia gas, the forward reaction is favored either by increasing the concentration of reactants or by decreasing the concentration of product. Understood? Yes or no? So either you add more and more reactants. So if you will add more and more reactants, so it will take the reaction in the forward direction. You will get more and more ammonia gas. The second way is that okay, whatever the ammonia gas is produced, you continuously withdraw, you continuously take out that ammonia gas from the system. And when you will continuously withdraw that ammonia gas from the system, so beta, the concentration of product will decrease as well. And when the concentration of product will decrease, it will favor the forward direction and it will produce more further ammonia gas. Understood? Yes or no? So which one do you think is more economical way to get the forward reaction? By adding more and more reactants or by continuously withdrawing ammonia gas? Which one is more economical way? Yes, because when you will add more and more reactants to get the forward reaction, so with the reactants, when you are adding more and more reactants, obviously you have to buy the reactants. So you have to spend the money on it. Yes, or no? Okay. So instead of spending money in adding more and more reactants to produce ammonia gas, what you can do, you can continuously withdraw the ammonia gas. Because obviously you want to withdraw it because you want to sell it in the market, yes or no? And if you want to sell it in the market, so you have to continuously withdraw it. So when you will continuously withdraw the ammonia gas, it will favor the forward reaction as well. And you will get more and more ammonia gas by these reactants. Understood? Yes or no? But ultimately, there will be one time when these reactants will get finished. And once the reactants will finish, all reactants are consumed, then obviously you have to add more reactants then to produce ammonia gas. Okay, but until the reactants are present in the system, you can take the reaction in the forward direction by continuously withdrawing the ammonia gas, by continuously decreasing the concentration of product. So it will favor the forward reaction, and more ammonia will be produced with respect to time. Understood? Yes or no? All right. Now the second one was temperature. Temperature. Now, can you tell me how temperature affects the equilibrium? First of, good. Good. We have to first check whether the reaction is exothermic or endothermic. Then we have to decide what temperature we should get to get more yield of ammonia gas. So, Haber process, you can see enthalpy change is negative. And if the enthalpy change is negative, it means that this reaction is the exothermic reaction. Okay. So for exothermic reaction, what temperature should we increase the temperature? Should we decrease the temperature to bring this reaction in the forward direction? Because we want forward direction, we want more and more ammonia gas. So what temperature should I keep? Okay, good. For exothermic reaction, if we decrease the temperature, so decreasing temperature will favor the forward reaction. And by decreasing the temperature, when the reaction will move in the forward direction, so you will get a higher yield of ammonia gas. So it means that for Haber process, the temperature should be kept low. Okay, understood? Yes or no? The temperature should be kept low. So over here we have written this statement over here. Okay, since the Haber process is an exothermic reaction, So according to Lee Chateliers principle, the equilibrium will shift to the right. Right side means forward direction. Okay. The equilibrium will shift to right if the temperature is kept low. Understood? Yes or no? Okay. So, so the optimum temperature which is set by the industry is 400 to 450 degrees Celsius. So this is the lowest temperature which is set by industry. Understood? Yes or no? How much temperature? 400 to 450 degrees Celsius. This is the optimum temperature for the Haber process, which is the least possible or the lowered temperature which should be kept for the Haber process. Understood? Yes or no? So you have to remember this temperature, 400 to 450 degrees Celsius. Now, there might be a question coming in your mind that why we are not lowering the temperature further from 450. We can further lower the temperature. We can cap it at 200. We can lower it down to room temperature as well. So why we have set the temperature up to 450? Why we are not lowering it down further? Because if we will lower down further, okay, so it will further take the reaction in the forward direction and more ammonia will be produced. Yes or no? Okay, because the more and more temperature you will lower down, it will take the reaction in the forward direction. So why the industries have selected up to 450 degrees Celsius? Why they are not further lowering it down? Did you understood the question? Yes, did you understood the question? Okay, the question is, okay, the optimum temperature which the industry have selected for the Haber process is around 450 degrees Celsius. Okay. Now the question is, okay, why they have selected this temperature? Why not 200? Why not 100 degrees? Why not room temperature? What is the problem in further lowering the temperature? Not really. Okay, let me tell you. Actually, when you will further lower down the temperature, so according to Lee Chateliers principle, it will favor the forward direction. Yes or no? If you further lower the temperature, it will still favor the forward direction, no? And you will get more and more ammonia gas. But the thing is that if you will further lower the temperature below 450, if you will take it to 200 or 100 degrees or room temperature, let's suppose. So, beta, what will happen? The kinetic energy of the particles will decrease. Yes or no? Because decreasing the temperature will decrease the kinetic energy. And beta, when the kinetic energy of the particles will decrease, so there will be less number of collisions. Yes or no? And because of less number of collisions, what will happen? Rate of the reaction decreases. Yes or no? The rate of the reaction decreases. Understood? Yes or no? So what will happen? Because if you will further decrease the temperature, the speed of this reaction, the overall speed of this reaction will lower down and the rate of reaction for forming the ammonia gas will decrease. So ammonia gas will be producing in a very slow speed. The speed of forming the ammonia gas will be very, very, very slow. Understood? And if it is very slow, so it means you cannot meet the market demand because in the market you want the ammonia gas to be continuously supplied. Yes or no? You want a continuous supply of ammonia gas in the market now? Yes or no? Okay. So in order to meet the market demand, you want ammonia gas to be continuously supplied to the market. So that's why you need a little bit speed for producing the ammonia gas. And for maintaining that speed, the optimum temperature which is selected is 450 degrees Celsius. Because if you will further reduce the temperature, the rate of the reaction will decrease. The time period required to produce the ammonia gas will increase and the ammonia gas production will be very slow. Understood? Yes or no? It will favor forward. You will get a large amount of ammonia gas, but you have to wait for it. You have to wait it for a very long period of time. According to Le Chatelier principle, if you further lower the temperature, it will favor forward. You will get more ammonia, but in order to get more ammonia, you have to wait it for a very long period of time, which is not desirable. Understood? Yes or no? So that's why we do not want a very high temperature, we do not want a very low temperature. We have selected the optimum temperature, okay, at which the rate of production of ammonia and the yield of ammonia both are balanced. Understood? And what is that optimum temperature? That is 450 degrees Celsius. I hope you understood the point, yes or no. Okay, so this is what is written in the last point. Okay, at a low temperature, the gases won't have enough kinetic energy to collide and react. Therefore, the rate of reaction would decrease. Therefore, compromise temperature of 450 degrees Celsius is selected. Okay, we cannot further lower the temperature. We will keep it up to 400 to 450 degrees Celsius. I hope you got the point. Any questions so far? Okay. Now coming to the third factor, which is the pressure. Okay. So can you recall how the pressure disturbs the equilibrium? What we have to first check before applying the concept of pressure? Okay, good. The number of moles on both the sides. So if you look at the number of moles on the reactant side, so it's 1 plus 3, 4 moles. Okay. There are total 4 moles on the reactant side, and on the product side, we just have 2 moles. Okay. So according to the industrial application, we want the reaction to go in the forward direction, right? Because we want a higher yield of ammonia gas. So what do you think? The pressure should be kept high or it should be kept low to favor the forward reaction? Correct. It should be kept high because the rule was by increasing the temperature, by increasing the pressure, the reaction goes in that direction which has less number of moles. So when you will increase the pressure, it will favor the forward reaction. Okay. So it means increasing pressure means you have to keep the pressure high. Understood? So since the number of moles on the product side is lesser than the reactants, okay, as we see in the above equation, the high pressure will favor the forward reaction. Understood? So optimum pressure, obviously, how much high pressure we have to keep. Okay, so industries have selected a standard, or you can say an optimum pressure for it. And the optimum pressure for the Haber process, which is set by the industry, is 280 M. So you have to remember this pressure value as well. Okay, what is the pressure? 280. So why we are not further increasing the pressure? Why we have kept up to 200 only? What do you think? Because if we will further increase the pressure, it will be advantage for us. We will get more and more forward reaction. So why we stop up to 200 only? Okay. The reason is written over here because of economical constraints. Okay. Actually, the thing is that for maintaining the high pressure, you need compressors. Okay. Have you ever seen compressors? You can find the compressors at the pump stations, okay? The fuel stations, the CNG pump stations. Over there, the large compressors are installed, okay? And usually you will find it in the industries. So in order to keep the high pressure, we need compressors for that, okay? And compressors, obviously, you have to spend money on buying those compressors, yes or no? Okay. So if you will, if you want to further increase the pressure, above 200, you need a large amount of compressors for that, a large number of compressors for that, and that would not be economical. Understood? That's all. Okay. Because if you will spend money on compressors, so you will not get that much profit margin by selling out the ammonia gas. Is it clear? Yes or no? Because your ultimate target is to get more and more ammonia gas. Yes or no? Okay. So if you will get more and more ammonia gas by installing more and more compressors, so that is not an economical way. Because for installing those compressors, for the maintenance of that compressor, you need a lot of money for it. Okay, and that will not be an economical way. So the optimum pressure is only capped up to 200 atm. That is what you have to remember. Is that clear to you? Yes or no? Okay. All right. Then now the last thing is catalyst. So obviously we would be needing a catalyst so that we can get the ammonia gas in a less period of time, so that we can increase the rate of reaction for producing the ammonia gas. Okay. All right. So, as you can see, we have compromised on the pressure. We have just kept up to 200 atm. Okay. So that compromisation can be covered by using a catalyst. All right. Or we have made a compromisation of the temperature as well. So that can be covered by using a catalyst also. Understood? Yes or no? Okay. So catalyst will speed up the production of ammonia gas, and the catalyst which we are using is the iron as a catalyst. Okay, so iron is used as a catalyst for any confusion or any questions so far. All right. Now, similarly, we have another application, another industrial application where we can apply all those four factors, and that is the contact process. Contact process. Okay, the contact process is also the one which we have studied already. Okay, contact process. The contact process is basically used for the preparation of sulfuric acid on a large scale. Okay, sulfuric acid. You know the formula of sulfuric acid, which is H2SO4. So in the industries, if we want to prepare this sulfuric acid on a large scale, we use this process, which is the contact process. Now, in the contact process, we have various steps. Okay, the first step of the contact process is there are two reactants, sulfur and oxygen. Okay. So first what we do, we burn the sulfur in the presence of oxygen to produce sulfur dioxide gas, SO2 gas. This is the step number one. Is it clear? In the second step, what we do, we further oxidize the sulfur dioxide gas. So the sulfur dioxide gas is further oxidized into sulfur trioxide gas, SO3 gas. Okay. And this step number two is your reversible reaction. The step number one was irreversible, but the step number two is a reversible reaction. Is it clear? Yes or no? And then when you will get the sulfur trioxide gas, so in the third step, you perform the hydration of the sulfur trioxide gas to produce sulfuric acid. Okay, you spray the water onto it and the sulfur trioxide gas to get the sulfuric acid. Is it clear? So, so the second step of this contact process is a reversible reaction. Okay. So in this second step, we have to apply all those four factors: change in concentration, temperature, pressure, and catalyst, so that we can get a maximum yield of this sulfur trioxide gas. We can get the maximum yield of this sulfur trioxide gas so that it can further be used to produce the sulfuric acid. Understood? Yes or no? So that's why we have picked up this second reaction. Understood? On this step, we have to apply four steps. All the four factors. Are you understanding the point? This one. Okay. Is that clear till now? Any question up till now? Okay. So we have to apply the factors of the Chatliers principle on this equation. Sulfur dioxide gas plus O2 produces sulfur trioxide gas. Now for this equation also the enthalpy change you can see is minus 197 kilojoules per mole, which is also representing that it is an exothermic process. Is that clear? Now let's start. First, change in concentration. Yes. So how you will change the concentration to shift the equilibrium in the forward direction to get more and more SO3 gas. Yes. Yes. It would be similar to the Haber process. Yes. Or either you increase the concentration of reactants to get forward, or you continuously withdraw the sulfur trioxide gas. You continuously decrease the concentration of sulfur trioxide gas to bring the reaction in the forward direction. That's all. Okay, so which is the economical way to continuously withdraw the sulfur trioxide gas? Understood this one. So SO3 is removed continuously to favor the forward reaction. Okay, all right. Temperature. Yes. What do you think? Temperature should be kept high or low to get more and more forward reaction? Okay, the temperature should be kept low. And how we decided it by looking if this is an exothermic reaction. So if this is an exothermic reaction, so for exothermic reaction, the temperature should be kept low to favor the forward direction. So again, for this one, you have to keep the temperature low. So how much temperature should I kept low? Again, the same principle we will apply as we apply in the Haber's process. So we have to select the optimum temperature, right? We cannot keep the temperature very, very much low. Okay, otherwise the rate of the reaction will decrease. Understood? We have to keep low, but up to a certain extent, we can keep it low. So up to a certain extent, if we keep it low, so we have to select some optimum temperature, and the optimum temperature selected by industry is 450 degrees Celsius. Understood? You cannot further lower it down because if you will further lower it down, what will happen? The rate of reaction will decrease. Understood? So we do not want the rate of reaction to decrease a lot. That's why the optimum temperature is 450 degrees Celsius. Understood? Yes, sir. Okay. Now, what do you say about pressure? Pressure should be kept high or low according to the scenario of the contact process. Okay, because first we have to see the moles, three moles of the reactant side and two moles of the product side. Yes. So what it should be? Yes, we should keep a high pressure or low pressure to favor the forward reaction. Yes, we have to keep the high pressure because increasing the pressure will favor the that direction which has less number of moles. So less number of moles are on the product side. So when you will increase the pressure, it will favor the forward direction. Understood? Where the number of moles are less. So the pressure should be kept high, yes or no? Okay. So what pressure was selected in the Haber process? 200 in. Yes. Over there also we have to keep the high pressure because the number of moles of the product were less. And the same scenario is in the contact process as well. But but the pressure, optimum pressure which is selected for the contact process is only 1 atm. Only 1 atm. We are not selecting like 200 ATM as we did in the Haber process. Over here, we are just selecting one ATM. And what is the reason? The reason is again the economical constraint. Actually, the thing is that if we are producing sulfur trioxide gas, yes or no, which is further used to produce sulfuric acid. Okay, so sulfuric acid is a very cheap product. It does not cost. It is not too much costly. Okay, it's a very cheap product. So the profit margin is also very low. So if the profit margin is also very low, so you do not want to keep a very high pressure because otherwise it would not be economical for you. Understood? Yes or no? That's why we just do the reaction of contact process at the normal pressure, which is 1 atm. Okay, we do not install compressors to keep 200 or above it because that would not be economical for us. Understood? For the Haber process, it's a little bit economical if you keep 200, but above 200, it's become not uneconomical. Understood? But over here, just 180 is enough. Is it clear? Yes or no? So you have to remember it. And the last thing is catalyst. So over here, iron was used as a catalyst, but right now we will use vanadium oxide V2O5 as a catalyst. So this is the catalyst for the contact process, which is V2O5. Did you got it? Yes or no?